Alright, today I've been working on simulating a Savonius rotor in Solidworks with flow simulation. So I have here a Savonius rotor with the offset blades. It's much more efficient to have that gap there. And the way the simulation is set up, first of all, it's set up as a 2D simulation. You can see we're not using the full height of the rotor as it is symmetrical on the vertical axis, so we can save a lot of compute time and reduce the number of fluid cells by doing that. We're using a rotating region in particular. This rotating region is the sliding, so the fluid cells in here are actually in a rotating reference frame, so everything in here is actually rotating in the transient simulation. So this isn't a steady state simulation, it's a transient. To get power, we're taking the surface goal torque of the rotor and multiplying it by the RPM and the constant to convert to power. And let me just show you our outputs here. So I started running. So you can see we got some what appears to be vortice shedding. And you can see our power. So it's peaking, which is interesting. It makes sense though, because when it's oriented along the long axis. Let me play it again, see if we can line it up. Right there. So it actually has what appears to be the peak power when the long axis is oriented. Actually, it's confusing me because I kind of figured a peak power. Oh wait, I think I'm just. Yeah, my eyes are just not following that well. Let's try this again. Peak. Okay, yeah. So this looks like the peak power is when the cup is facing directly into the wind flow. The wind flow is 4 meters per second or 9 miles per hour, relatively low wind speed for the simulation. So, the flows all look right. Everything looks like it's changing, how I'd imagine wind to. We can also look at, I ran a bunch of parametric simulations. So first of all, I went through a few different sizes. The big one is what you just saw, huge, or the huge one is what you just saw. It's about 2 feet across. Tiny one's about 1 foot across. And here's their power outputs and torques plotted with rotation speed. So the way the simulation works is the wind's not what spins the rotor. The rotor has a forced rotation from the rotating reference frame. And what we can do, right, is we can look at the torque and we can say, okay, that torque's being resisted by, say, a generator, and we can use that torque and that RPM to generate power, to get a power. Right, so where torque would be 0, so here, you can see where there's no power, that would be the sort of steady state rotation speed. So the huge one would, if it had nothing loading it rotationally, it'd spin at 18 radians per second, which is roughly 180 RPM, so 3 times a second. And then if you loaded it for maximum power, you would be spinning about 60 RPM, or once a second. And you'd get about 3 watts out of it, according to the simulation. So a few things, just to make sure our calculations make sense. You can see we have about double the power, and we have double the area. So just a quick thing to mention, our rotor here, it's about 2 by 5, so about 10 square feet of area, right? The smaller one, it only changes in the width. It's about half the width, so half the area. So we expect half the power since the energy in the wind is linearly scaled with area. So that makes sense that that's happened. Also, the bigger turbine, for the same wind speed, is going to take longer to rotate. So we can see it's got a slower spin rate than at the maximum power point than the smaller one, which can, cover more distance in a smaller spin. So for the same wind speed, it should spin faster. And we have our torques. We can see that our torque from the huge one is a lot more than our torque from the teeny one, which also seems to make a fair bit of sense. They don't scale linearly, which I kind of expected. Maybe it just has to do with how the fluid dynamics work out, but yeah, the torque does not appear to scale linearly, interestingly enough. Alright, and so the next step here is going to be simulating the huge one, multiple times. So instead of just simulating the 5, we'll simulate the big one at different wind speeds. So for that, we're expecting sort of a linear ramp up, right? Since energy is velocity squared, we should pretty quickly get to no power as we go down in wind speed. So it'll be interesting to see how this all works out. What'll also be interesting is seeing how it makes sense to match this to make a hybrid with a Darius turbine. Those are another vertical axis wind turbine, but they need to be spun up to start working when there's wind. So people hybridize them, and they use the self-starting of the Savonius to enable the Darius to start spinning. And I suspect their maximum power points aren't going to work out well. It's also pretty hard to simulate the starting torque. That would be the lower RPMs, so we can actually look at that here. Yeah, you can see it's got a decent starting torque. So that torque is what's going to spin up the other rotor, and that one has higher efficiency and moderate wind speeds. So hopefully the hybrid will help it work in lower wind speeds. But yeah, hopefully once I have graphs for the Darius turbine, I can compare them to the ones I've simulated for this Savonius, and I can find the best size to match between them so that they can, have good starting torque and hopefully match peak power points. Yeah, that's all I have.